An experimental analysis of EMI shielding effectiveness using multi-layered metal meshed reinforced sustainable foam. Abstract organic foams are fabricated using a general mixing process incorporated with fine grid metal mesh inside it. The physical and chemical properties and the electromagnetic shielding effectiveness of these foams are investigated. The FTIR results indicate the presence of different organic functional groups. The sample with copper mesh was found to have the best EMI shielding effectiveness, followed by brass, iron, and steel meshed samples. The average return loss in dB for a single layered sample with copper mesh was found to be around 28.715 dB, and the average shielding effectiveness was found to be around 29.006 dB in the range of 8 to 12 GHz. The multilayered mesh samples showed better results than single layered samples. Keywords: organic foam, electromagnetic interference, EMI, shielding, frequency, fine metal mesh. Introduction. The increasing complexity of electronic devices or systems in the form of higher packing density for quick response has resulted in electromagnetic interference. 1. Electromagnetic interference, EMI, or radio frequency interference, is the noise that is resulted due to unwanted radiated signals caused by a wide range of electronic devices. The problem of EMI becomes prominent with the increase in the complexity of electronic devices or systems which has a high packing density for a quick response. Thus, it not only affects the performance of the device but also causes its degradation too. So, it becomes important to research on the performance features of the potential EMI shielding materials 3 to 5. The material chosen must not have any unfavorable impact on the performance of the equipment. It should not trade off the efficiency of the equipment with the EMI shielding or hinder any of its workings. So other properties of the material such as flexibility, mechanical and thermal stability must be decent enough to give it a real industrial application and not just theoretical concept. 6. 11. Considering all the factors, reinforced organic foams are believed to serve the purpose. They are lightweight, flexible, and eco-friendly. 4 samples are synthesized with organic foam as the base and different metal meshes, steel, iron, copper, brass, as the reinforcement. Various techniques are used to obtain the properties of the samples, and a shielding effectiveness test setup is used for testing the EMI shielding capability of the material. A comparative study has been carried out to contrast with different samples. 2 experimental proceduria. Fabrication of meshed foam samples are prepared with single, double, and triple layers of steel, iron, copper, and brass mesh reinforced in flexible foam. First of all, some identical wooden molds are created with 5 sides closed and 1 side open. The open side is mounted with a fixture for holding the mesh of grid size 1 mm in the middle of the mold. The walls of the mold are waxed to facilitate the easy removal of the foam after preparation. After fixing the metal mesh on the fixture, a mixture of isocyanides and polyol of ratio 2:3 is put into the mold and the reaction is allowed to take place. The reaction is exothermic and carbon dioxide gas is released as a byproduct. In the multi-layered meshed foams, the distance between the adjacent meshes is 3 mm. A. Brass mesh, B. Copper mesh, C. Steel mesh, D. Iron mesh. Fig. 3. Different metal meshes. B.EMI shielding test setup. The electromagnetic interference, EMI, shielding effectiveness is measured by using an experimental setup consisting of a transmitter transmitting radiation of 8 GHz, 12 GHz and a receiver. A spectrum analyzer is used to generate a plot of the shielding effectiveness, SE, of the sample being tested. In this setup, the transmitter and the receiver are placed 30 cm apart excluding sample thickness, and the sample is placed in between as shown in the photograph. The plot is obtained on the analyzer for the frequency range of 8 GHz, 12 GHz. 3. Formula. The theoretical quantification of EMI shielding effectiveness as expressed in the literature 7 to 10 are as follows. Transmission coefficient, T, equals S21 superscript 2. S21 equals spectrum parameter of different PU foams, or also called the return loss. Shielding effectiveness, SE, total equals 10 asterisk log, 1/t, dB. 4. Results and discussion. A. FTIR test. According to the plot obtained from the Fourier transformation infrared, FTIR, spectrum, we have verified the functional groups present in the different foams. The plots obtained is shown below. Flexible foam, in the below graph, we can observe the broadening of the peaks in the range near 3500 cm1, which confirms the presence of O functional group. The stretching of the peaks near the range of 3000 cm1 confirms the presence of CH groups. The absorption in the range of 2165-2110 cm1 shows the presence of cyanide group. B.ME shielding performance test. The result of the ME shielding performance test was obtained in the form of a graph as shown in figures 8, 9, 10, 11 and 12. The results have been summarized in Table 1. The negative value of shielding effectiveness merely represents the loss of M wave power concerning the incident M wave. The comparison should be made based on the absolute value of the shielding effectiveness. According to the graphs obtained from the ME shielding effectiveness experiment, the foam with the copper mesh was found to have the maximum shielding effectiveness, followed by brass, iron, and steel sample. The single-layered samples have little less shielding effectiveness in comparison to multilayered samples. And among all, the samples with copper mesh have better SE, followed by brass, iron, and steel, which is around 32 dBs. Conclusions. The physical and chemical properties of the samples are found, and the shielding effectiveness is characterized using the ME shielding test. The sample with copper mesh was found to have the maximum shielding effectiveness, followed by the sample with brass, iron, and steel meshes. Multilayered samples have little more shielding effectiveness than single-layered samples. The mock inability of the shielding material is improved because of the meshes. Now it is easy to shape the shielding material into different shapes and retain the same. Thus, we can derive from our investigation that in the frequency range of 8 GHz 12 GHz the flexible foam with different meshes can be actively used to provide effective shielding for satellite communication body parts covering radio navigation and data transfer and operations. As brass alloy has better SE, T in comparison to pure metals such as iron and steel, so this research work opens the gate for further investigation. Acknowledgement. We are thankful to VITechNI for providing us with resources and fully equipped laboratory for carrying out the experiments. We are also thankful to the mentor, guide, co-author Dr. Gianthi Subramaniam and her research scholar Mr. Yuvraj for helping and providing us with basics and knowledge for the study of the results and its development.